Okay, hi everyone. Thank you for turning up to my talk. This is awesome. Privileged to be up here. So I'm going to run through Kaskada, which is how to do real-time AI. A little bit about myself before I start. I am a Apache Cassandra committer and PMC. Last year, I was the PMC chair for that project. At work at DataStax, I am the VP Product OSS. That is pretty much just looking after the operations of how the company contributes and coordinates with all of the different actors and contributions going into open source projects. The open source projects that we work with, particularly Pulsar and Cassandra, have quite rich communities in them with multiple companies and vendors in them. Originally, I was an engineer. I was an engineer for a long time and by trade. And for 10 years before this year, I was a consultant, and I've worked with some of the largest Cassandra deployments around the world. We're talking about NASA, Woods Hole Ocean Institute, and the big telecommunications, the big banks, etc. A little bit about myself personally. I am Australian, as you may have heard. I live in Norway. I met a wonderful Norwegian woman, and I have a family there now. My first time in Croatia was last year. I went to Loped and Dubrovnik, and absolutely loved it. The Australian in me feels like he is home again. The warmth weather, the warm people, the salt water. You could add some waves, that would help, but you've got a few thousand years of history and culture. Small difference there. We've got the dreaming. A little bit more about the company that I work for, DataStax. We run not just Cassandra in the cloud and as a service in any cloud in any region, but we run an application layer data platform. And that consists of many components. And the value of that you will get through this presentation. I'm going to break this talk up into 4 sections. I'm going to talk about Kaskada and what it does. This is why you turned up. I'm then going to go into generative AI and RAG apps. I'm going to build you an AI chatbot in 5 minutes to show you how simple it is. And then I'm going to combine both real-time and generative AI. And hopefully, if I've got time, I'll talk about some of the problems that this stuff will face in production. So first up, Kaskada. There are many different types of machine learning. The machine learning or the AI that we're talking about here is that which is based on time. Forecasting, trends, detecting anomalies as they happen. This is essentially event processing. And Cassandra is about creating an abstraction layer to make dealing with these types of things simple and fast. Not just simple and fast, you will see that with Kaskada, you can do a number of things that simply weren't possible or at least weren't feasible to do previously. Is the volume a bit loud? Yes, no? It's good? Okay, Kaskada has a lot of features. I'm only going to touch the tip of the iceberg in this presentation. I really recommend, it is a rich library already. If it's interesting, I recommend that you go check it out afterwards. Probably my favorite feature is the native time travel. I think a lot of ML platforms in the next year or two, the ability to be able to do time travel for accountability and auditing is going to hit us more and more. Also, one of the founders of Kaskada is Croatian. So he was an engineer at Google for a long time working on their ML platforms. And he recognized that this was really the missing piece in technology for most companies to deliver up to half of their value out of ML platforms. Okay, so winding it back and going, starting with the basics. So a timeline. It's essentially ordered data grouped by entity. On the x-axis, we have time. On the y-axis, we have some value. Entities here, people, grouped by color. Nothing fancy, pretty traditional and popular way to represent data. If we want to aggregate data, for example, we want to say how much did each user spend over time. Then we just create a sum of each timeline. Again, nothing too fancy here. This just kind of highlights the difference between a discrete timeline and a continuous timeline. You can do this in SQL. Let's continue with this. What about, sorry, that was the previous example. And that was how we do this in Kaskada. So it's just a simple one-liner. On the purchases, on the amount column, we want the sum. Not complicated. What about how much has each user spent this month? Again, it's really simple in Kaskada. The same line, but in the sum function, we're simply passing in the window since the month. What about if we want to aggregate not on time, but on some other arbitrary event or data? This is one of the tricks that Kaskada is pretty good at. So what about the case where, just give me a second. What about how many page views? What about the example? How many page views does each user normally have since the time they purchased something? So here we can see we're looking at a number of different timelines. We're looking at the page views. And we're looking at the purchases and then resetting the count when there's a purchase. In Kaskada, how we do this is page views, counting since the purchase. If we're going to do this in SQL, it's possible, but it's already quite complex. In Kaskada, it's one line, super simple. So this is what the library has been built for. Another example we can jump through quickly is temporal joins. What is the average product review at the time of a purchase? So here we want to look at take the reviews scores, associate them by each item, compute the average, and then look up each purchase. I'll go through that again. Take the reviews, get their score, associate them with each item, take the average, and then look that value up by the purchase item. Try and do that in SQL. It gets pretty complicated. SQL is just not built for this type of stuff. There's stuff in this which I didn't know existed. And if, as an engineer, I came along and had to fix someone else's SQL like this, I would have a heart attack. So we don't want that. You can say maybe this is just unfair comparing it to SQL, but if we have a look at Spark streaming, and we take a real-life example for churn prediction over time, we took an existing example that Spark had, and it was 63 pages long, and in Kaskada, we did it in 2 pages. You see, this framework makes it super simple. Kaskada library has a Python interface. So far on the slides, what you have seen is snippets of Python. But underneath, the whole engine is written in Rust, and it keeps the data that it's processing in Apache Arrow. So it's able to use GPU where it can. Some of you may be familiar with DuckDB, which is quite popular at the moment and known to be very fast. benchmarking it against DuckDB, we are consistently faster. And in some situations, an order of magnitude faster. So you may be sitting there going, well, there's no machine learning yet. Where's the AI? Yeah, essentially, we're still talking about taking feature stores here to feature engineering. This is something that's kind of been laid on top of different ML platforms today. If your feature store is more rich, those traditional predictive ML solutions have a lot of advantage. I'm going to lift and shift that and apply it to what we're working with this year, 2023. To do that, I'm going to go through an example RAG app. If you don't know what a RAG app is, it's retrieval augmented generation. What I mean by that is, you know, we've seen lots of presentations, and you'll know about how to use ChatGPT and put in prompts. What we're talking about here is, before that, we've got a prompt template with variables in that, and we want to generate a prompt based both on long-term memory and short-term memory. Our long-term memory is where we take all of our in-house or proprietary data and we vectorize it. We choose some embedding model or sentence transformer. We create embeddings for it using a sentence transformer or whatever we want, and we put it into a vector store. So then when the user comes along and asks a question, we create an embedding for that question. We then do a vector search and get the 3 closest questions from our internal database, and then put that into the prompt and get a response. This reduces hallucinations, and it ties the answers and the results from the large language model, which it can be served from somewhere else, for example, OpenAI, to our data domain. Let me run you through an example. If I go to datastax.com, I'm going to open up Astra. This is why I wanted to be on the other Wi-Fi, but it's what I've got for now. That bounced on me at the last minute. Okay, so I'm in the Astra console. I have already created a database for this demo. It is otherwise empty, but I've just called it the RAG chatbot DB. Okay. And on here, there are some examples. If I go to an example, this is going to open up another page. I've got this page open already. I can show you what it looks like. That ain't it. Sorry. It's one of those examples that are listed on that page. And it's going to take you to this Jupyter notebook. I'm going to run through this Jupyter notebook and explain how to set up an application that follows the architectural diagram that I just showed you before. Where's that? Okay, so first of all, got to reconnect. While I'm waiting for that, first step, I'm going to install some Python libraries. Python's not my favorite language, but it's pretty popular in this audience. I'm going to import a few things, the Cassandra driver, OpenAI. I'm going to grab the database model there. Okay, so I'm connected. So let's install those Python requirements. I have already done all of that. Let's do my imports. Done. Okay, so here I need an Astra DB token. We get that when we go into the Astra database. where we go to connect, and then we go get an application token. I've already got one, so I'm going to just take mine and copy it in. Next step is I need my OpenAI key. To do that, I'm going to go to OpenAI, log in. Under your settings, go to View API Keys. So this is platform.openai.com, and you got a key there. So I've already got that here. I'm going to just copy it myself. Okay, and the last one is the key space that I'm using. And in my database, the key space that I had set up already was, this rag chatbot key space. If I've already got focus there, I do. Okay, so I'm still setting up some variables here. Since I've got a token, that's going to be my method of authentication. Now I want to go and I need to grab the connect bundle to connect to the Astra database. Again, you can get this from the connect tab in Astra. Second option there, get bundle, that will give you a zip. Let's say I get a client application to connect. And so what I'm going to do is go find that file. There it is. Good to go. The sentence transformer that I'm going to use to create my embeddings, text embedding Ada. Okay, test a connection. We're good to go. In case I've got any table in the database already, get rid of it. And this is the table I'm going to use. ID, which is just a unique identifier. It's just a random unique identifier, no meaning. Title, the context of the question, and then all the possible answers. And then I'm going to create a vector on that information and store it in the same table. So I do that. And then I'm going to create an index on this vector column so that I can do my vector search. Okay, now I'm going to download the Stanford the question answering data set. That's what I'm pretending to be my company's proprietary or in-house data that I'm building my expertise off. Done. Let's take a quick look. It looks good. Here we go, like titles, context, the question, all the possible answers. I know that this data set has duplicates, so I'm going to get rid of them. They do not help me. Now I'm going to go through all of that data and create embeddings for it and add those embeddings next to my original data in a table. This will take a little while. While it's running, the next step will be, so I've got that all set up, ready to go. Now imagine a chatbot UI, and the user goes to that chatbot UI and they ask a question. And the question that they're going to ask is, when was the College of Engineering in the University of Notre Dame established? I will take an embedding of that question, do a vector search, and then all put it into a prompt. Okay. No, it's still running. Good time for a drink of water. while that's still running. So this is what we're going to do with that, the vectorized question. We're going to do a select statement from our table. And this is how Cassandra and Astra will do a vector search for you. You're simply saying, I want this, I want the 3 closest columns by a vector search to the embedding that I pass in. So I'll get 3 rows which were closest to that question. There are further options in here that I could have put in the create table schema around like the similarity function, equaling or cosine or dot product. So I wonder how many are there. So it should drop out of 300. Oh, it's done. Fantastic. Let's keep going. Get the question. Create an embedding of it. That's my vector. Over 1,000 dimensions. Create the query first. So it looks like it's all of the vector, but at the beginning you can see that select statement there, down the bottom. I underestimated how difficult it would be to use the mouse on a second screen. Okay, and if I just want to have, I'm going to execute that query and take a look at the 3 closest questions. So these are 3 questions that I found that by vector search were close. So then what I'm going to do is I'm going to create my prompt. And here the system is your chatbot helping customers with questions. The user is a customer with their question. And I've got an assistant with 3 example questions. Let me run it. College of Engineering and the University of Notre Dame was established in 1920. So in roughly 5 minutes, I've generated an AI app for you. Okay, moving on. None of that had anything to do with Kaskada. So where is the value of bringing Kaskada and a RAG app or generative AI together? Let's look through a few examples of types of questions that you may want to use against a large language model. When will my package arrive? Or what should I watch tonight? Or is now a good time to buy Bitcoin? You'll see that a lot of these questions are going to be based on data that you will have to get from other places. More so, we'll see that some of this data actually needs declarative reasoning on timelines to get you to the right answer. For example, on the Astra console, we have a chatbot there that helps users support with their databases. And a user called Ben comes along and he says, why are my queries against the database so slow? With no information about what he's doing, what his current intent today or in the session is, even the large language model is going to give him a pretty generic answer. Hey, Ben, queries can be slow for many reasons. For example, the service may be under heavy load, or your query may involve significant computational costs. Well, duh. I'm pretty sure Ben knows that already. What if we can put some real-time context in that? What if we know that the average query latency is around 5 milliseconds, but currently he's got about 7 seconds on his queries, and we can pull out what his recent queries that he's executing are. That is enough to land us in the right place. Let's go through another example. I can't demo this, I don't have time. I'll do it as fast as I can. Slack is a wonderful tool, but I think a lot of us, certainly me, is finding it next to impossible to keep on top of all the different accounts and the hundreds of channels that I'm now a part of. And it's kind of this like, do I just completely give up and ignore it? Or do I just kind of dedicate 10, 15 minutes every day reading hundreds of messages across all these channels and looking for that one thread that I should be involved in to help out? What if we can create a Slack bot that can just send me notifications? Hey, this is a thread that you would usually participate in. For example, like this. And we're calling this the Beep GTP. Beep, maybe interested in this conversation, go check it out. Pretty neat, pretty nifty. How that would work is we would take a dump of a Slack account or the data, and we would feed it through Kaskada to re-put it into timelines. And then into a predefined format, like a prompt, we will fine-tune our large language model or OpenAI large language model, GPT with it. This example introduces fine-tuning. That's kind of like an extra thing. Fine-tuning is not something you typically need. Just prompt engineering, 90% of the time will get you what you need. But there are some use cases where fine-tuning is useful. And then once we have that fine-tuning set up, we can then just have a little bot that listens to all the messages in a Slack account, put it through Kaskada. Kaskada will generate that same predefined format, put it into a prompt, and then the response to GPT will tell us which users are most likely to respond to that message or thread. This project is on GitHub. It is under the Kaskada AI organization. It's called Beep GPT. It essentially consists of two files. There is a fine-tuning Jupyter notebook, which does the top path, just about give me a dump of data from Slack. I'm going to put it into Parquet files. Then I'm going to generate the timelines from it. Then I'm going to, using Kaskada, put it into these predefined formats. And then you've got this Beep GPT Python file, which is the bot that just listens to the messages as they come in. All right. So in the fine-tuning, it's about a page long, but this is the most important part. This is the Kaskada part. It's super simple. It's just taking the messages and it's creating records on them, joining on the channel and the thread ID. So we get threads. And then you'll see in the Beep GPT Python file the exact same Kaskada code because it's got to recreate the same predefined format. Okay, running out of time, going to move quick. So you can see here that both RAG applications, super simple, super powerful. You see with Kaskada timelines, super simple, fast, super powerful. And you connect these two things together, pretty legit. And we're seeing, especially this year with AI, large language models, the democratization and commoditization of data science and machine learning. We're not needing to train models anymore. Any old programmer can come along and build this stuff. Pretty cool. But once it's in production, and now anybody can do it, what are the next problems that we're going to hit? Well, first of all, we're going to look at how do we think the production of the architecture stack is going to change. This is what we're seeing so far already. At the bottom layer, you have the data tier. The data tier or the data platform is becoming the most important part of engineering and an application stack. I'm not talking about analytics. I'm talking about your application platform today. The definition of digitalization changed this year. Last year, digitalization meant the automation of tasks and processes. This year, it means just getting analog data into a digital state, into a tier where it's democratized, and you have a single control plane over it, and you can just put AI apps on top of it, and they can go crazy. On top of this, you have all the integrations that you're going to need. I've given you a few examples of them. On top of that, we've got business logic and user experience. We're going to see UX really change up. Making a phone call, that's going to be engineering, and talking to an AI bot, that's going to be a valid UX now. And more so, these layers on the top are becoming cheap and commoditized. So they're the ones that the AI can do for us, so long as we have this in place. What that means is this layer here. We'll be working with less data, but the data must be in the application stack. the need for copying all of our data into the analytics platform will have less demand because we will be able to do more and more directly in the application layer. And when we can do it in the application layer, a lot of our data will have a much shorter time to live. So a lot of engineering platforms will actually see smaller amounts of data in their platforms. This is why we use Cassandra as a component in our data platform, because it's scalable and it's linearly scalable, which is really important for businesses because they need to predict their growth as they grow, predict their costs as they grow, but it's also elastic. I'm out of time, so I'm going to jump forward to my thank you slide. This is the compulsory product slide. Thank you to my company for paying for me to come here. I know it looks like a product slide, but there's actually something else I want to say about this slide. Open source is essentially about the commoditization of technology. A true open source project is not a single maintainer project on GitHub. That's what I like to call egos on parade. It is not a company open sourcing their code under their copyright. That is marketing for transparency marketing, or just a bait and switch technology. As soon as they have enough critical mass, they have no further interest in continuing their contributions to open source it. True open source is when you have a copyright to a foundation or to a third party, and you have multiple companies involved in that technology. That is a commoditization of technology that benefits all of us. You may not be an active open source contributor yourself, but the message that I want to give to you is that when you go and pick products, when you go and pick the companies to deliver the products for you, take a look at how much those companies are contributing to open source, how much they are helping commoditize technology for the better of all of us. Thank you.